Hi everyone, this is Keeley and we're going to talk about Atwood machines today. An Atwood machine is basically some masses tied together with a rope and a pulley. And in this case we have two masses set up so they're arranged like this, so they're vertical. And we have mass 1 that's 5 kilograms, mass 2 that's 8 kilograms. The pulley has negligible resistance and its moment of inertia and stuff like that. We're not going to worry about that. And we're just simply going to find the acceleration of the system. Well, to start off, let's take a look at what would be the free body diagram for this. And so for this, both objects will have gravity acting upon them, but M2 is more massive, so it will have more force from the gravitational field than the other one. So we're going to make that arrow a little bit longer than the other one. But it also has a tension on it. Now this is where we have to pay attention. The tension is the same for both of them, because the force on this rope, since that's just one continuous rope, is the same everywhere in the rope. So these two arrows should be the same length. This one should be longer because it's more massive, so it weighs more. This one should be slightly shorter because it's less massive, so less weight. And so this whole thing should rotate this way, or I should say this side should fall and that side should rise. And now that we got the concept or the idea down, we need to actually figure out how much acceleration it has, and maybe even find the tension in the rope. And I always like to find the tension in the one that's going up. But let's take a look at this. Now, there's a couple different ways you can do this problem. I'm going to solve it the way I like the best, which is one that you don't see in textbooks very often because I'm not bright enough to understand that one, but I can remember this one. And it goes like this. The force that's causing the movement is equal to the force on the system. Okay? And so what's causing this to move is the difference in the masses of these two objects, or basically the weights of those two objects. If they weigh the same, this would essentially stay still. But since one is heavier than the other one, that's going to cause that one to fall and the other one to rise. So it's actually the difference in the two weights. So I'm going to write it as M2, in this case, minus M1, because M2 is the more massive one. If M1 was the more massive one, I would put it first. And then the system is both M1 and M2 accelerating together. If I set it up that way, then I can actually figure this out pretty easily. So at this point, we can just kind of plug in the numbers. So that is 8, that's 5, gravity's 9.8. Again, we're going to do 5 plus 8a, and then just solve at that point. So we're going to have, this is basically 3 times 9.8 equals 5, 8, 9, 10, 11, 12, 13. A, there we go. 3 times 9.8 divided by 13 gives me an acceleration of 2.26 meters per second squared. So that's the acceleration of my system. To figure out the tension, like I said, I like the one that's going up. And the reason why I like that is because the equation makes more sense in my head that way. So to figure out the tension, we're going to pretend this other side doesn't exist. We're just going to worry about this side going up with that acceleration. So basically we're doing MA equals the sum of the forces. Well, we're talking about this one right here. So it's accelerating upward, tension is upward, weight is downward. So we're going to have MA equals tension going up minus the weight of that block, and that's block 1. And so I just plug in my numbers here. We got MA equals tension minus mg. Mass of 1 is 5. Acceleration was 2.26. equals tension minus 5 times 9.8. Move that across. So let's go ahead and calculate that out. So I'm going to just go ahead and do all the numbers. 2 times 2. I'm just going to calculate all the numbers. 5 times 2.26 equals 11.3. 5 times 9.8 gives me 49. Add that to the other side, and we get our tension in the rope to be, that's going to be 60.3 newtons. Just double checking. And so the tension in the rope is 60.3 newtons. Now that would be the tension on either side, because it's a single continuous rope. So the tension in one place is the tension everywhere in that rope. But I find it's easier to find the one that's going up. Even if they ask you the one that's going down, it's still easier to find the one that's going up. Just makes more sense to my head. Let's talk about how we can make this problem a little bit more interesting. So what if we have multiple masses? So in this case, we've got 3 masses. And we've got M1, that's 3 kilograms, so we'll put a little 3 there. M2's 5. Total 8 on that side. That one's 4. Okay. So, on this one, we've got the weight of this one going down, so Mg3. This one, that's more weight. That's 2. This one's not as big, so that's Fg1. Now for the tensions, here's where things get a little bit more interesting. The tension for this one is going up. The tension for this one is going up. And these two should really be the same. But the tension for this one's going to be slightly smaller. So I'm going to call those two same. I'm going to call these that one and that one. Let's call this one 2. The reason why is this is one continuous rope. So the tension in one place is the tension everywhere. But this is a separate rope. And this rope is really only dealing with that mass right there, not both of them together. So this one only has to deal with that one. So the tension should be a little bit less. All right, so let's actually calculate this using that same process that I just went over. The force that's causing the movement equals the force on the system. So the force that's making it move has got to equal the force on the system. All right, now what's making it move is, again, the difference in weights on both sides. Well, this side is more massive, so it's also heavier, so it's going to lower and that side's going to go up. So I'm going to say, when I write my equation, I'm going to say M1 plus M2 minus M3 G, because it's the weight of them, equals the whole system, which is M1 plus M2 plus M3 A. And we solve it. Just plug in the numbers. And so we got 3 plus 5 minus 4 times 9.8 equals 3 plus 5 plus 4A. And we just solve for it. So this would be 4 times 9.8 equals 5, 9, 10, 11, 12, 12A. And we just do the math. 4 times 9.8 divided by 12 gives me an acceleration of 3.2, let's call it 7 meters per second squared. Again, there's another way to solve this problem, going back more to using the free body diagrams, but that can get a little wonky. I like this one a little bit better. It's more consistent for me. Now, let's see. We want to find the tension for this rope here. Now remember, anytime you're asking for tension, just block everything out. Just think about what's happening to that rope and what it's doing. So that rope is lifting this 5 kilogram mass, or lowering that 5 kilogram mass. The reason why it's lowering is because this side's going down, right? And so we're still going to do MA equals the sum of the forces, but we need to define what's positive and what's negative. Do we define up's positive and down's negative, or vice versa? In this case, let's go ahead and say that down is negative. Now this is accelerating downward, right? Because that side's falling. So that means that we're going to have MA, and that A is going to be negative, equals the tension is acting up, so that's the positive direction, minus the weight of that block. And so MA equals T minus MG. And that's negative because we already said down's negative, so I already took care of that with that sign there. And so we get 5 times negative 3.27 equals T minus 5 times 9.8. And so 5 times 3.27 gives me that this is negative 16.35. Tension we don't know. 5 times 9.8, 49. That's going to be added when we put that to the other side. So I want to subtract off the 16.35. And we get the tension in the rope here to be 32.65 newtons. And it's positive because that tension is acting up. So it makes sense. But whenever you're trying to do this, like if I want to find the tension in this one, and I wanted to talk about that, I would just cover this up, and this rope is having to deal with both these masses. If I want to do this one, I know the acceleration going up, and that rope has to deal with this mass lifting it. So you only concern yourself about that rope and what it's doing to whatever it's attached to. Let's try one more where we change the situation up one more time. And we've got this one here. So basically very similar to the very first one, except we got this table, and for this one, we're going to say the friction is negligible. If we did have a friction term, that would affect its motion. But let's say we don't. And we've got that M1 is 8, M2 is 5, M3 is 4. All right, so if I want to draw a free body diagram, this one's only a 4, so it has some gravitational force, some weight. This one should have about twice as much more. Not quite drawn to scale. This one also has a force down, its weight. Also has a normal force acting up that we could use if we actually had friction. And we have tension. We have tension going up here, but that is also pulling on this rope this way, the same amount. Likewise over here, this tension should be the same as those, and this one's also pulling this way. Now what's causing this block to move here is not this, well, it is the tension in the rope, but really it's the difference in the two weights that's actually doing that. So these aren't killing each other off and so nothing moves. The actually reason why it's moving is because the difference in the weights of these two masses that's hanging off the edge. So we still want to do force that's making it move equals the force on the system. What's making it move, again, is the difference in these two weights. So I want to say M1 minus M3 in this case, G, because it's different in the weights, equals the system, which is M1 plus M2 plus M3, A, because this is moving the entire thing. And again, we just plug in the numbers. 8 minus 4 times 9.8 equals 8 plus 5 plus 4, A. And then we just start working through the math. 4 times 9.8 gives us 39.2. 12, 13, 14, 15, 16, 17. 17A divided by 17 gives me an acceleration of 2.3 meters per second squared. Now, if we had friction, that would be an additional term on this movement side. So we would have m1 minus m3g minus the friction of that block on the table. And so that would reduce our acceleration. All right. Well, there's Atwood machines. Tune in later and we'll do modified Atwood machines. Thank you and bye.